Hello, everyone. This is lab group number 7 from MAE 318 System Dynamics and Control. Today, we're going to be talking about our electric vehicle speed control system. For this presentation, first, we're going to introduce ourselves, then we're going to discuss about the lab objectives, the design process, recommendation to customers, and finally, the summary.
I'm Dustin Hofer. I'm a mechanical engineering student here at ASU.
I'm Nathan Goldsmith. I'm also a mechanical engineering student at ASU.
And I am Javier Gomez, also a mechanical engineering student here at ASU.
So the lab objectives and specifications from the customer is to recommend a controller type for our customer. In this case is Soco. They produce EV vehicles. The goals of this lab is to get an accurate model, produce a controller that has no steady state error, fast response time, good transients, like no overshoot, and among others, and not require an insane amount of voltage. So the next part of this is the controller design process. It consisted of 6 steps. The first one is to model the system mathematically. We did this through theoretical derivation. Next was to lay out the design specifications, and then after that we collected experimental data to model the constants of the system, like the DAC relationship to the motor. We experimentally found the DAC relation, or experimentally found the resistance of the motor, the minimum voltage to start the motor, the transfer function from the between the controller and the motor. We then simulated the controller design and tested that on a physical setup. We experimented with a proportional integral controller, a proportional derivative controller, and a proportional integral derivative controller. And through all that process, we used MATLAB and root locus to find our final transfer function.
That iterative design process that Nathan just went over led us to a PI controller, a proportional integral controller, that gave us great results. We were able to reach a speed of 12 rads per second with 0 error. We were able to reach that speed in under 0.2 seconds, and we have no overshoot at all. The voltage response was also well within the desired specifications, the maximum being 14.5 in our system, and the maximum requirement was 24. In the graph below, you can see that the experimental results match the theoretical results almost perfectly, proving the robustness of our model.
The results of this lab led us to recommend a proportional integral to control the motor with modifications to the transfer function. A PI, proportional integral controller, it's very important because of its ability to manage steady state values and also to manage steady state errors and dynamic errors. This lab only modeled and experimented with DC motors, and the results should be similar with AC. If they aren't, however, the same lessons can be applied. This design process will work for many other systems in the car, anything with a motor.
Thank you for listening.
Thank you very much.
Thank
All
you.
right.